In this example, you're being asked to determine which molecule is the most reactive electrophile for an SN2 reaction. And just like the first two, I got to remind you, in an SN2 reaction, you have some sort of nucleophile attacking some sort of sp3 hybridized substrate, carbon, and kicking out a leaving group simultaneously. So when we look at these three molecules, we need to think about what is different about these substrates. And we can see that this one on the left, no fluorines. This one here in the middle, it has 2 fluorines, and this one on the right, it has 1 fluorine. First thing we want to remember, keep this in mind, that carbon-fluorine bond is a relatively strong bond. Fluorine is basically never a good leaving group. Fluorine is not a good leaving group, okay? So no nucleophile is going to come in here and kick out the fluorine. Well then, okay, that kind of makes us wonder, well, which carbon is getting attacked then? Is it the blue carbons with the fluorines on them? Let me put a blue dot on there. No, because fluorine is a terrible leaving group. Okay, what about those carbons of the double bond, which I'm going to dot in orange? Is that where the nucleophile is going to attach? The thing is, a nucleophile could come in and attack those carbons, but nothing's going to leave except the pi bond. Those are reactions you'll learn about later. For now, SN2 reactions, they only take place on sp3 hybridized carbons. So all of these carbons that I dotted in orange here, they're all sp2 hybridized. So that SN2 reaction is not going to occur on sp2 hybridized carbons. So it's not going to be those orange ones there. All right, well, what about these carbons that I'm dotting in red? Is that where the nucleophile could potentially add? Could something come in here and kick out a leaving group of some kind? Well, think about it. In an SN2 reaction, they work best on substrates that are not sterically crowded. So methyl substrates, primary substrates, they work much better than secondary, and tertiary substrates don't work at all for an SN2 reaction. So those red carbons I have dotted there, those are primary carbons. Question is, what would the leaving group be in this scenario? So let's take this first molecule, the one on the left. Okay, and let's just draw this thing again. And I'm just going to be really generic, and I'm just going to write nucleophile. Okay, just some sort of species with negative charge that can attack some sort of partial positive charge. Okay, so that oxygen on this substrate is pulling electron density from this carbon. That's going to put a partial positive there. Now let's imagine what happens if this thing came in and attacked. If that attacked that carbon, that would kick out these electrons on that oxygen. And when it does that, we now have this leaving group. Okay, we have that leaving group plus the species that just formed, which I'll draw that out here, but we're not really too concerned about that. That would be the nucleophile now bonded to that methyl group, okay? Not really too concerned about that. What I want to focus on here is this leaving group, okay? So that's an oxygen leaving with negative charge. We have to keep in mind that why is that a decent leaving group? Well, because that negative charge can move here, which kicks the charge up there. That is a resonance stabilized negative charge, okay? And the more stable that negative charge is, the better leaving group it will be, all right? So in that first reaction, that is what the leaving group would be. All right, what about the other two reactions, the one in the middle and the one on the right? Let's draw all of these potential leaving groups, okay? So I'm going to redraw the first one. Then I'm going to draw what the leaving group would be in the middle one. And there's that negative charge. And then I'm going to draw what the leaving group would be on the last one. And so our job here is, let's compare these three leaving groups, okay? Because some sort of nucleophile is going to come in, attack those red carbons, kick out those leaving groups. The best electrophile is going to be the one that has the best leaving group here. Well, what's different about these? They all have that same amount of resonance. That negative charge can move into this carbonyl, and that just moves that negative charge between the two oxygens. They all have that same amount of resonance. But what about induction? What could stabilize that negative charge in conjunction with the resonance? Well, fluorine, let's look at this closer. Fluorine is pulling electron density away from this carbon here, which in turn is going to pull electron density from here. And that's actually going to help to pull the electron density that is building up on the oxygen. So that molecule in the middle has two fluorines using an inductive withdrawing effect to stabilize that negative charge. This molecule over here, it has one fluorine doing that same thing. That's going to help stabilize that negative charge. Not as much as this molecule is, because it has two fluorines doing that. And then the one over here, it doesn't have anything pulling electron density inductively to help stabilize that. So the one that would be most stable here as a leaving group would be this one, which means this molecule will be the fastest to react in an SN2 reaction because its leaving group is stabilized the most.